And if you plot that, the time for rupture and stress, then it looks like a straight line, and if there is a change in activation energy, then it changes the slope. Okay? And this phenomena can be resembled in this type of equation. So if we assume the relation between the time and the temperature can be taken in this form at constant stress value. So if you change the stress value, your activation energy, the slope of the line will be changing. So this is basically, if you do it in log terms, then the logarithm of ln t, if you plot versus 1 by t, then it will be a straight line, and the slope of that line will be q by r, which is shown here. So if you do it at different values of stresses, what you are getting is you are getting different straight lines with different activation energy values, which is q by r, and that is a function of stress. Okay? And this can be used to find out the parameters at a longer time. So for example, if you want to know the strain rate at 10,000 hours at 540 degrees Celsius, in order to do that, if you do the stress rupture test, you only have to do it for 13 hours at a little higher temperature. Okay? And then you can calculate the properties at this condition, and we will see how that is done. Okay? So here the intercept, so all these lines, if you do the testing at different stress values and you put the specimen under the load, under constant stress, and let it fail, and then you plot the temperature versus the rupture time at constant stress, you get a straight line like these. Okay? So you do it at obviously different temperatures, and that's how you get this straight line. So you do many tests at different temperature until failure, and you draw these lines. So it was found that they all converge at single point, and that single point is negative on ln t axis, which is called minus C1. That value is minus C1, and C1 usually for these materials were found to be 46. Okay? And this is not Larson-Miller parameter. This is a constant value, ln theta. This is Sheridan parameter. Okay? So theta is Sheridan parameter, which is related to minus C1, which is nothing but the intercept of this line. Okay? But what you can do is you can plug ln theta is equal to minus C1 here, and then you get this equation. Okay? So if you put minus C1 instead of ln theta, then you get this equation. And if you say that the q by r ratio is constant, and let's say that constant is P1, then obviously t into ln C1 is going to be constant, right? So this is ln t. This is ln of time plus C1. C1 is a constant which is known, which is 46. Okay? And if you know this, then you can know the temperature, and we will see. So you do this testing at different stress values, and then you plot the curve, and then we will see how that curve looks like. So if you plot P1, and P1 is called Larson-Miller parameter. Okay? This is called Larson-Miller parameter, and this is simply T into ln of time plus C1. Okay? And C1 is 46 usually. So if you plot this, if you plot on x-axis the Larson-Miller parameter, which is T into ln of T is rupture time, and then you plot on x-axis, you plot stress in megapascals. Okay? So what actually are you doing? You are doing a lot of tests. Just to get this one, C1, you have to do many tests at different temperatures but constant stress. Then you find out what is the value of C1. But C1 usually is 46, so you can ignore that part. Then what you do is you do testing at different stress values. Okay? And at each stress value you find out the rupture time, and using this equation at different temperatures you find out the value of Larson-Miller parameter. Okay? Or what you can do is, you can do the testing at different stresses, keep the temperature constant, still you will get different Larsen-Miller parameter because time of rupture will be changing with the stress. Okay. So you can both change temperature as well as stress, but you will still get a single curve. And because you get a single curve, it means that a single curve can describe the material's behavior at different temperature as well as at different stress. And that is why this curve is called a master curve. Master curve is a generic name. It is not unique to creep. There are many master curves. So basically it means that there is a curve which is defining more than many properties. So this is a master curve. So you change the alloy or you change many variables, but you still get a single curve, and those kind of curves are called master curves. So you do testing at different temperature and different stress, you will still get all the data points which will be following this curve. Okay. So we will do a quick example of this, which is also given in the textbook, but just for the understanding we will try to do this quick example. So let us say that we want to find out the stress at 100,000 hours. We want to find out the stress at which the material will fail at these many hours. So do you want to do the testing at these many hours? If no, then you find out the Larsen-Miller parameter, plot this curve and extrapolate it. And then you can solve this. You can find out at which stress the material will fail. Okay. So you want to know that at which stress the material will fail at these many hours at a temperature of 650 degrees Celsius and at a temperature of 870 degrees Celsius. So basically in this equation you must remember that temperature is always given in terms of Kelvin and not in degrees Celsius. So this is very, very important. So what we do is, let us say that at 650 degrees Celsius, if you calculate P, what will happen? So 650 degrees Celsius will be 923 Kelvin and 870 degrees will be 1143 Kelvin, right? So I put P1 at 650 will be equal to 923 into ln of T, and T we know is 100,000 hours. We want that what will be the stress required if it fails at this. So T is known, so T you can put 100,000 plus C1 is known, so that is 46. So we can calculate P1 at 650, we can calculate P1 at 870 degrees Celsius, and now we know P1. Okay. So we know P1 and then we have this curve, so we can straight away find out that which stress we will have to apply so that the material fails at those many hours. So what are we doing? The testing we are not doing at 10,000 hours, but still we can get the data. We only have plot, let's say for this one, but we know how it is, so we can extrapolate that and we can find out that at longer time how much stress will be required for the failure. With this we end this lecture here and we will continue in the next lecture. Thank you.